Good morning, ladies and gentlemen. I hope you're having a great day. Can you believe it is already Thursday and already second period? I'm sorry I don't get to be there with you today, but hopefully having virtual me there is even better. As I was looking over the homework that you guys had for today, really I don't see anything on there that I think you guys will need great explanation to. My guess is that most of you, if not all of you, were able to look at the problems and work through them successfully. And if you got a little bit wrong, when you check the answer in the back of the book, you could probably see where you went wrong. What I'd like to do is I'd like to take a quick look at probably what is the most complicated problem in that section and just to kind of make sure that even with something complicated like this, we see how ultimately how easy it is. So this is 37b, and 37b has this big quotient or fraction that has all these negative exponents within, and then it's the whole thing's being raised to a negative exponent. And so what I want, before you think about, well, I got to deal with all those negative exponents on the inside, what I would encourage you to do is really deal with this negative exponent on the outside, but in a different way than maybe what we would think. You got to remember that if I have a negative exponent on the outside, if I have x over y and the whole thing's raised to the negative 2 power, that is the same thing as y over x all raised to the 2 power. And the negative goes away. But that's not what I'm talking about. I'm thinking about the fact that you can distribute that exponent. If I had something like x over y all raised to the 3rd power, that's equal to x to the 3rd, y to the 3rd. Or even if I had x squared over y raised to the 3rd power, that would be x to the 6th over y to the 3rd. And so in that situation, I'm going ahead and I'm distributing that exponent to each part. And that's really what I think you should do over here. Is if you take care of that first, a problem like this actually becomes way easier, okay? So I'm going to distribute that exponent to each part because I know that a negative times a negative is a positive. So as I distribute that -1 exponent to each component of this whole thing, then almost all the negatives are going to go away. And so here's what I would get as I'm doing it. As I distribute that exponent, I'm going to end up with q to the 1st power, r to the 1st power, s to the positive 2 power, and then on the bottom I'm going to have r to the 5th, s to the -1, and q to the positive 8. And so the only negative I have left is that one on the bottom, that s to the -1. So that gets moved up top, and so then this would look like q r s squared times s all over r to the 5th, q to the 8th. Now at this point, I can kind of combine and then do my subtraction based on what I have up top and down at the bottom. And so on the top, I can see I've got QR, and then obviously s squared times s is going to give me s to the 3rd power. So I'd get QR s to the 3rd power all over r to the 5th, q to the 8th. And at this point, obviously the q's and the r's are going to cancel out to some degree. And so I've got 1, or to the 1st power on the top of each one of those. So really all that's going to do is that's just going to subtract 1 from each one of these exponents right here. And so the whole thing then should simplify down to just s to the 3rd power over q to the 7th, r to the 4th. And that's the final answer. And so even though this thing looks super complicated to begin with, you see that it really wasn't that bad, especially if we take that first step to distribute that negative exponent, make almost all the negatives go away. And then I took my time solving it step by step, and I get to a real easy solution. And so this was probably the most complicated problem of the section, so I think you guys are probably going to be fine. I don't think it's really worthwhile for our time for us to work through every single one of those. If I was there today, I bet there might be 1 or 2 questions I'd work through, but I think it'd just be kind of wasteful of time to work through all of them. Okay, so at this time, you can go ahead and let's see, what do we want to do right now? It would be good to turn in your homework. Okay, so that way I can check it. Excuse me. I can check your homework when I get it, but go ahead and turn it in. Please understand that I am looking for some level of work. This is homework, not home answers, but right now, go ahead and turn in your homework, and then we will get started at what we get to do. All right, let's go ahead and get started. So today, the name of the game is rational exponents and radicals. Rational exponents and radicals. And so if, let's do a basic quick review. The word rational. Now the word rational in real world means makes sense. That's rational, that makes sense. Rational in math refers to a type of number. A rational number, most people think fractions or decimals, and that's pretty correct. The definition of a rational number is it's any number that can be written as a fraction of two integers. So even like some, never-ending decimal like 0.6666666 over and over and over, that can be written as a fraction of 2 over 3. And 2 and 3 are both integers. And so this is a rational number. If I have a real simple decimal, something like 4.5, well, that can be written as 9 over 2. But there's no matter what I do, like something like the square root of 2 can never be written as the fraction of two integers. And so this is an irrational number. So when you hear the word rational, a good idea is to typically think fraction. When people are talking about, hey, we're going to do this with rational exponents, they're probably using that thinking we are going to use fractions of some sort, whether they be improper fractions or proper fractions. So we're going to have fractional exponents and radicals. That's what we're looking at today. Okay, so we're going to do a real quick basic review on radicals, and I'm going to remind you of the rules of radicals and roots and work a couple problems with each rule. After that, I'm going to give you some examples to do, and then I'll work through those examples, making sure you're all set. And then we'll get to talk about those rational exponents. Okay, so first of all, let's talk about the rules, the basic rules of radicals, okay? And so there are 5 basic rules, and they're pretty simple. I'm not going to do an example after each one. We're just going to kind of go through these pretty quickly. Okay, first of all, the first rule would be that if you have a radical that is really two things being multiplied by each other, where basically you can factor some value into two separate values, well, then you can take that radical and you can actually break it up into two separate radicals. Now, that might not make a whole lot of sense, but if you think about, say, a larger number that you don't know the square root of, something like, say, the square root of 256, and you're like, I just don't know what that is. But let's say you were decent enough to know, you realize that that's an even number, and it's an even number, you cut it in half a couple times, and you realize that that's the same thing as 4 times 64. Well, at this point, one of the things that you could say is, well, then that would mean it must be the same as the square root of 4 times the square root of 64. And so now, all of a sudden, I'm looking at the square root of 256 in a different light. I'm looking at it as the square root of 4 times the square root of 64. Well, the square root of 4 is clearly 2, and the square root of 64 is 8. And 8 times 2 is 16. So that really answers my question to what is the square root of 256? Well, it's 16. So that's pretty simple. And now, so you can see sometimes it's going to be worthwhile to take something that could be factored out and break it into a couple different roots or a couple different radicals. But please understand that this also goes the other way. You can go from here to here. Okay, this property goes frontwards and backwards. And by that, what I mean is, if you had something that says the square root of 27, which I don't know, times the square root of 3, which I don't know, when I multiply those together, I get the square root of 81, which I do know. The square root of 81 is 9. And so sometimes it is also good to bring two of them together because then I will know the square root. I did skip a little mini step there, that the square root of 27 times 3. Hopefully you saw that it went from here to ultimately this answer here. All right? So that goes frontwards and backwards. All right. So now let's talk about some of the other rules. All right. The next rule. Next rule would be kind of the same thing, but in terms of fractions. So rule number 2 would be if I'm dealing with the nth root, and the reason I have n there is because this could be the square root or the cubed root or the quad root or the quint root or something, 5th root, 6th root, whatever. And if I have some root of a fraction, a over b, well, that can be written as the nth root of a over the nth root of b. Again, that might seem a little bit weird as we look at it, but think about that. There's times where I've got a fraction, and that it, as a fraction, it can seem a little bit complicated. Like if I had something like the square root of 16 ninths. And I go, man, I don't know square roots of fractions at all, but if I realize that that's the same thing as the square root of 16 over the square root of 9, well, that's easy. Square root of 16 is 4, and the square root of 9 is 3. And so now all of a sudden that's 4/3. And so that becomes an easy answer. But remember, just like before, you can go backwards. Okay, sometimes it makes more sense to go backwards, and it doesn't seem that way, but sure enough, it does. If I had the square root of 32 divided by the square root of 2, see, I don't know the square root of 32, I don't know the square root of 2, but when I put it all as one fraction and I get 32 over 2, that becomes the square root of 16, which is 4. So sometimes it makes sense to go forward on this rule, and sometimes it makes sense to go backwards. But the good thing to know is that a fraction can be split into two radicals, or a fraction of two radicals, as long as they're the same power or root, can be combined into one big fraction. You can go frontwards or backwards. All right, moving on. The third rule. The third rule is like combining roots. If you have a root of a root, that sounds crazy just to say it, but if you had, say, something like the mth root, that's hard to say, of the nth root of a, that's the same thing as the m times n, or times n, I'll get rid of some of this. There we go, made it a little bit too long, of a. And that's pretty complicated. We're not going to see a ton of this, but it's definitely one of those rules we got to know. Okay, and what we're saying here is if we had the cubed root of the square root of some given value, whether it be a variable or some number that we know. Let's just put in a 3 there. I don't know the square root of 3. But ultimately, if we have the cubed root of the square root, well, that would be the same thing as the sixth root of 3. Okay? Because I can multiply those two values, that 3 and that 2, resulting in a 6. So I'm looking for the sixth root of 3. Now, I don't know what the sixth root of 3 is, but either way, that's kind of what we would get in this situation. All right, let's move on. The fourth rule. Almost done, guys. Got 5 main rules of properties of roots. And so here we go, the fourth rule. The fourth rule is a really simple one. It says that if you take the nth root of a to the n, you get a. Now this is true only when n is odd. Now, it seems like this would be true all the time, but this is only true when n is odd. And I'm going to show you what happens when n is even. But so what am I saying? I'm saying that if you have the cubed root of negative 3 raised to the third power, well, that would be the same thing as the cubed root of negative 27, which is negative 3. And so see, that value that was inside here at the very beginning is the one that became the answer right there, okay? And so that value just came out. And I basically, in one sense, I could say, well, I just kind of canceled those the exponent and the radical out, and I'm left with the negative 3. And this would work even with positives, of course. It's not just exclusive to negative values. If I had the cubed root of 8, that is the same thing as the cubed root of 2 cubed. The 2's cancel out, and I'm just left with, the 3's cancel out, and I'm just left with 2. There you go. So, now that works for when n is odd. When n is even, the rule is a little bit different, okay? So here's the last property or rule of these roots. The fifth rule is going to be, what do we do when we're talking about the nth root of a to the n when n is even? And this is what's weird. You got to kind of think about this. Before I write what the rest of that is, I want you to think about it. We typically think, well, the square root of 4, and we would say, well, that's the same thing as the square root of 2 squared, and so that is 2. And so we get in this habit of going, well, the square root of 4 is 2, and that's true. But that's us making a small assumption. We're assuming that it was positive, when actually the square root of 4 could have been positive or negative. It could have been negative 2, Because ultimately, inside this part right here, we could have written that as the square root of -2 squared, okay? And so then we would look and go, well, wait a minute, but I assume that it's +2. Well, here's the thing, is when we do square it, what's inside does become positive. This right here would simplify down to -2 times -2. And so therefore, -2 times -2 is the square root of 4. And therefore, we go, well, the square root of 4 is 2. So here, what we're looking at is we're going, the square root of 4 is 2. But see, I started with a -2 on the inside. So I can't look at this top example right here and say, so therefore it is always equal to A. Because it's not, okay? Because initially on this one right here, let's see, we'll go, on this one right here, my A value was -2. And yet my answer is +2. Okay? And so when these are even, when the root and the power are even, what's going to happen is every time you're going to get the positive version of that number. Okay? It doesn't matter if that number was positive or negative to begin with, you're going to get the positive version of that number in the end. And so what that means is, what's the positive version of a number? The absolute value. So what that means is, instead of me leaving it like this rule right here, instead what I would say is that the nth root of a to the n is equal to the absolute value of a when n is even. There you go, when n is even. Okay, so those are our 5 basic rules, and those are pretty simple. What I want to do right now is I want to work through a few examples to try to make sure everybody's understanding where to go on this. Okay, so first, let's take a look. And I'll do my best to stop coughing, even though I'm not present with you guys. I know it sure still bothers you. Excuse me. All right, okay, so let's look at example number 1. Exemple numero uno. So example number 1, if I had something that said, let's say, the third root of x to the 4th, okay, and I had to simplify that. Well, there's a few different ways to think about this, but I would go back to that first property or that first rule, and I say, wait, I can split that up. This is the same thing as x to the 3rd times x. That's another way of thinking about x to the 4th. And now I've got the same value here as I do here, and they're both odd. So that number just comes right out. So that x to the 3rd would come out as just an x, leaving inside 1x. And so that would be my final answer right there. That might seem a little bit oversimplified, but it's that easy. Okay? Now, if I had almost the exact same problem, but it was with a square root, so if we call that exemple numero uno, that's part A, and then part B could be, well, what if I had a square root? And then the root is even at that point. And I said, let's say x to the 5th. Excuse me. Let's do that better. Instead of x to the 5th, let's say x to the 3rd. We'll make it almost the exact same. So that would mean I have the square root of x squared times x. And we know that that x squared can come out of the radical, but because our values here and here are even, then it comes out as absolute value of x times the square root of x. That's what's left inside. All right? Because of course on a regular square root, there's actually like an understood 2 right there. All right, so that's example number 1. What I'd like you all to do right now is I want you to try to do 2 problems very similar. And what I want is you to find the cubed root of 8a to the 5th. And if you finish that one, I want you to find the fourth root of 48a to the 7th, b to the 4th. Okay? All right. You can pause the video right here. Everybody give that a shot, and in about 90 seconds or 2 minutes, we'll take a look at it. Okay, hopefully that was enough time and you are ready to go. All right, so let's talk about how I would do this. Well, for this one right here, for the first one, I've got the third root of 8a to the 5th. And so you go, well, that's pretty simple, because if you didn't know this, 8 is the same thing as 2 to the third power. A to the 5th is the same thing as a to the third power times a squared. And so really this comes out and simplifies real easy. That 2 to the third power comes out of a third root as a 2. That a to the third power comes out of the third root as an a. And the a squared is left inside. So I'd have the third root of a squared. That's pretty simple. Okay, now for this next one, this one is a little bit different because here I've got an even root. All right, and this number matches this number right here, and it's going to match what we're going to break this into. So this one is going to be the same thing as the fourth root. And we can think about how in the world are we going to break up 48? Well, 48 is the same thing as 16 times 3. And then a to the 7th is the same thing as a to the 4th times a to the 3rd. And then b to the 4th is just b to the 4th. And so that might not have seemed like that helped a whole lot, but 16 is the same thing as 2 to the 4th. So we have 2 to the 4th times 3 times a to the 4th times a to the 3rd times b to the 4th. And this is all the fourth root. Well, now we have the fourth root of something to the 4th and something else to the 4th and something else to the 4th. And so those are all going to come out that way. Okay. Now we don't have to take the absolute value of that 2 because when we write it on the outside, we're writing it as a positive 2. But I will have to take and write the absolute value of that a and that b when they come out. And so this is going to be 2 absolute value a b, and then so this came out, this came out, and this came out. So then we got to kind of take inventory and see what's still in there. That 3 is still in there, and the a to the 3rd is in there. So we'd have 3 a to the 3rd. So this would be the answer. Hopefully you got that. All right. Well, now let's take a look at combining radicals. Okay, and this is going to use some of the properties we talked about, but this is going to be something maybe you haven't done before ever. So let's try this. This will be exemple numero dos. Exemple numero dos. Here we go. All right, with exemple numero dos, you can have something like the square root of 32, which I don't know, plus the square root of 200, which I don't know. And using that first property of breaking things up into their factors, I can do already some work with this that then helps me simplify the whole thing. See, the square root of 32 is the same thing as the square root of 16 times 2. And the square root of 200 is the same thing as the square root of 100 times 2. Well, I know the square root of 16. That gets to come out. Now, I don't think I have to write the in-between step, but you know, if you wanted to pretend there would be another step, you could say, well, the square root of 16 times the square root of 2 plus the square root of 100 times the square root of 2. I'm kind of skipping that step because I think we all see that. And so instead, I'm just going to go ahead and pull the 16 out and say, well, that would be a 4 times the square root of 2. And we're going to go ahead and pull out this 100, and that would be a 10 times the square root of 2. Well, at this point, when you have an unsolved radical like this right here, you really treat it as you would a variable. So you kind of treat square root of 2 as if it were an x or a y or a z. And so this becomes kind of like 4x plus 10x. And that's a real simple one to solve. 4 square root of 2's plus 10 more square root of 2's would give you a grand total of 14 square root of 2's. That's simple. And that's a whole lot nicer looking than this big ugly mess at the top. It's nice to be able to realize that that simplifies down to something as simple as 14 times the square root of 2. All right? Now, I think with that said, let's have you try to do a couple just like this. okay? So break out your paper and pencil again, but I'm assuming you've hopefully been writing most of this, if not all of this, down so far. All right, so here's your problems. I'm going to give you two. Let's say the square root of 75 plus the square root of 48. And then also, we'll say the square root of 16x plus the square root of x to the fifth. Now, please understand, look at how I did this last problem. Notice that at no point did I reach for a calculator to grab what this is, okay? Because that's just going to be some ugly decimal, all right? That's not going to help the process here. If I plug this into the calculator, I'm just going to get an ugly decimal for this, an ugly decimal for this, and even one for this. I have to do this using my brain, all right? I have to do this by following the properties and simplifying. And so right now, as we look at the square root of 75 plus the square root of 48, don't be tempted to grab a calculator and think that that's going to be an easy way of solving this. It's just going to make it uglier. So go ahead and pause the video right now. I'll give you guys a couple minutes to give this a try, and we'll go over the answers. All right, well, let's take a look at it. Hopefully you look at this first one and go, man, that's really easy. When I see 75, I think of 3/4 in my pocket. So that's 25 times 3. When I think of 48, unfortunately, there's no money to go along with this, but it breaks down just as simply, and it's 16 times 3. So the square root of 25 times 3 plus the square root of 16 times 3. Well, we know the square root of 25. The square root of 25 is 5. So I've got 5 times the square root of 3 plus, we know the square root of 16 is 4. And so we say 4 times the square root of 3. And now I just have 5 square root of 3's plus 4 square root of 3's. And that gives me a grand total of 9 square root of 3's. All right. Let's look at the second one. And this one might seem a little bit odd or a little bit different, but you go, oh, this is not too bad. Okay. Let's see here. You would have 16 times, or square root of 16 times x plus the square root of x to the fifth. Now, remember that there is an understood 2 on both of these, because something's going to happen on these that might confuse you a little bit. Some people may have used absolute value on these, but you didn't have to. Okay, and let me show you why. First of all, this is the same thing as the square root of 16 times the square root of x plus the square root of, let's say, x squared times x times x. All right? And so let's kind of think about this. Obviously, the first one, square root of 16, that's easy. So you get 4 times the square root of x. The second one, now think about this. I would have the absolute value of x, that came out, times the absolute value of x, times whatever's left, and that's the square root of x. Now at this point, whether x was positive or negative, when I multiply it by itself, I would get a positive. So I don't have to write the absolute value of x. This is kind of a step that would not need to be written because this would be known. When x came out, because I have to then multiply it by itself, even if it was a -3, when it comes out, it's going to be a -3 times a -3 on the outside. That's going to make it positive. And so really, this step that I just wrote is a completely unnecessary in terms of this other part right here. Really, what I would do is I go from here, I would say, well, this is 4 times the square root of x plus x squared times the square root of x. Okay, because one x came out and then another x came out, and that would be x squared. And so I don't have to worry about this whole absolute value thing because there were 2 of them out there multiplied by each other, so therefore it had to then be positive. I don't have to worry about it being absolute value. Okay, so now I've got 4 times the square root of x plus x squared times the square root of x. Now here's the only downside, is I really can't do a ton to combine 4 and x squared. They're not like terms. But using the distributive property or factoring, I can kind of bump that square root of x off to the side, and I could rewrite it like this. 4 plus x squared all times the square root of x. And at least it looks a little bit simpler. And so that right there would be my final answer to this problem up top. All right, moving on. Hopefully you guys are doing it as well as I hope and think you are. Okay, so we're going to move on to the idea of rational exponents. Okay, rational exponents dealing with, let's see. I lied. We're not going to deal with rational exponents yet because I want you guys to practice this a little bit, okay? What I'd like you to do is I want you to turn to page 29 in your books. And if you don't have a book, Miss Avent has a sheet for you in lieu of a book. But what I want you to do is I want you to turn to page 29, and I'm going to give you a handful of problems to do. Not that many, but I want you to try some of these to try to see if you're kind of getting it or not. These are going to be a review of the practice of really what we've done. And so what I want you to do right now is go to page 29, and I want you to work through, let's see here. How about 17 through 23? Now look, at every one of these problems has part A, B, and C, but I'm not going to ask you to do that. What I want you to do is I want you to do part A, okay? I want you to do 17 through 23. I think I can make a better 2 than that. 17 through 23, odds, only part A. And this will give you just a chance to kind of work through a few problems in a row and try to feel good about them. And so what I'm going to have you do is I'm going to have you pause the video right now. I'm going to give you somewhere around 5 or 10 minutes to work on these because I don't think it's going to take that long. And then what I'll do is I'll go over them briefly, and hopefully at that point you'll kind of be ready to rock and roll. We can take a look at fractional or rational exponents. All right? So get going on 17 through 23, only the odds and only part A. All right? Good luck. Okay, hopefully at this point you are feeling pretty good about what you had and you made a lot of sense because a lot of these problems were really, really simple. So let's talk about them. 17 simply said the square root of 16. Oh my goodness, okay, that is easy. That's 4. Okay, number 19 says 3 times the cubed root of 16. At least this one's a little bit more complicated. And so you think about, well, what is the cube root of 16? Well, I don't know what it is, but I know that this simplifies down to 3 times the cube root of 2 to the 4th power, because that's what 16 is. And I could simplify that down to 3 times the cube root of 2 to the 3rd power times 2. And 2 to the 3rd power, the cube root rather, of 2 to the 3rd power is 2. So I'm going to have 3 times 2 times the cubed root of 2. 3 times 2 is, of course, 6. So I get 6 times the cubed root of 2. A lot of work for a real simple problem, but I just want to make sure I don't miss anybody or any step, okay? Now let's take a look at number 21. 21 says, I love this one, the square root of 7 times the square root of 28. See, I love this because I have no idea what the square root of 7 is, and I have no idea what the square root of 28 is. But yet this problem simplifies so easily because I can combine them to 7 times 28. Now that might not make your life seem a whole lot easier at this point because you go, wait a minute, 7 times 28, that's 196. And maybe you don't know the square root of 196. Now, I do. Yay! But you might not. Okay? So then there would be a different way to do this. You could break 28 down. You could say, well, wait a minute. This is the same thing as 7 times, and 28 is the same thing as 7 times 4. Okay? So now all of a sudden, I have a couple 7s in there. It's like saying I have the square root of 7 squared times, and I know the 4 is 2 squared. So then those two values could come out. I could say, well, then the square root of that would be 7 times 2, which is, of course, 14. And so that right there then must be the square root of 196. And it is, okay? The square root of 196 is 14 because math is true and stuff. All right? So anyway, hopefully that problem you saw, that was a pretty simple way to go. Maybe you didn't catch that one, but that's all right. Okay, lastly, number 23. Number 23, pretty simple, and I'm sorry that I gave you guys 5 to 10 minutes to work on this. Hopefully you guys started the video sooner than that because obviously these did not take that long. But the last one, number 23, is the square root of 216, which I don't know, over the square root of 6, which I don't know. But this simplifies to one big fraction or one big radical. You could have the square root of 216 over 6, which is then, if you divide 216 by 6, you get 36. And the square root of 36 is 6. Wow, what an easy problem. Okay, looks super complicated in the beginning, but it ends up simplifying to something so simple. All right, now with those done, everybody's kind of taking a quick mental break for a second. What I want to do is I want to take a look at this idea of rational or fractional exponents. And we're going to work through a couple examples on those and hopefully make some sense of them. Okay, so this idea of rational exponents is really quite simple, okay? Here's the idea. There's two ways of thinking about it. It's a to the m over nth power. You could say that that's equal to the nth root of a raised to the mth power, or you could also think about it as it being the nth root of a raised to the mth power. It doesn't matter. And that's the best thing about rational exponents, is that you can change this order based on what's easier for you. Sometimes the top situation is going to be a little bit easier, and sometimes the bottom situation is going to be a little bit easier. I'd say usually the top, but there are going to be some times that the bottom might be the way to go. Okay? And so now let's put in some numbers and some values with this to help this make some sense, because as it is, I'm sure this looks absolutely hideous. What I want to do is tell you first off, this number up top, you are going to always treat that like an exponent. Notice where that showed up. It showed up here. It showed up here. It's an exponent. Okay? This one is an exponent. But this number on the bottom, you're always going to treat that like a root. Notice where that number showed up. Here and here. So then, this is real simple. If I say I had x to the 2/3, I got to remember that that top, the 2, is like an exponent, and the 3, the denominator, is like a root. So this is the same thing as the cubed root of x squared. Or you could write it as the cubed root of x, whole thing squared. It doesn't matter. It's literally the same thing. Okay? So the top is the exponent, and the bottom is the root. Okay, with that said, now let's take a look at some of these problems. There's one little catch on these that is in your book, and so what they do is they don't want to start bringing in all that absolute value and trying to go, okay, when is it going to be absolute value? When is it not going to be? They just, even your book says, hey, what we're going to do is we're going to say if n is even, and look at what n is. Remember, n was the root. If n is even, then we require, it's almost like they're making a little assumption here, we require that a be greater than or equal to 0. That way we don't have to even worry about that whole absolute value business. Okay, let's just deal with this as much as we can. Okay, rational exponents, these are simple. All right, so let's go. In terms of rational exponents, let's look at an example. I think we're up to what? Exemple numero tres, if I'm correct. Okay, so exemple numero tres, we'll do 3 parts. We'll start with a super easy part. We'll say part A is 4 to the 1/2 power. Okay, now think about that. The top is the exponent, 4 to the 1 power, that's easy. And the bottom is the root. 2 is the same thing as the square root. And so we'd say the square root of 4 to the 1st power, which is just the same thing as the square root of 4, which is 2. Wow, this is simple stuff. Part B, ready? We have 8 to the 2/3 power, all right? And this one, I look and go, okay, there's definitely a couple different ways to do this. I could say that this is the same thing. Remember, the top is the exponent, the bottom is the root. So I could say that this is the same thing as the 3rd root of 8 squared, or I will write down a little bit further, this is the same thing as the 3rd root of 8 squared, okay? Now, honestly, I like this second one a little bit better. Either one is doable, but I like the second one a little bit better because it kind of keeps it small. I know that 8 is the same thing as 2 raised to the 3rd power, okay? And I'm taking the cubed root of that. Well, the cubed root, those just kind of cancel each other out, and I'm left with 2 squared, which of course is 4, okay? Now, it wouldn't be different to do it the other way, but I could look and say, well, this comes out to be the cubed root of 8 squared. 8 squared is 64. And I just might not realize what 64 is. 64 is 4 cubed. So again, these cancel out and I'd be left with 4. Check it out. Math is true. It doesn't matter which way you do it, you're going to get the same value. I really recommend you just do it whichever way is easier in that situation. Okay, and lastly, hey, come on. This wouldn't be fun unless we threw what? A negative in there. So if we said 125 to the negative 1/3 power. What? I know. And so think about what that would be. Well, first thing I'd have to do is I'd deal with that negative. And 125 to the negative 1/3 power is going to be 1 over 125 to the 1/3 power. So the first thing we did is we dealt with that negative exponent. A negative exponent is a mover. It moves it to the opposite part of the fraction. And then you say, well, 125 to the 1/3 power, what's that going to be? Well, it's going to be the cubed root of 125. The cubed root of 125. And if you're not sure, 125 is the same thing as 5 cubed. So there you go. Those 3's take care of each other, and you're left with just 1/5. So 125 raised to the negative 1/3 power ends up just being 1/5. That's pretty simple and easy. All right. Well, let's see here. Wonder if it's your turn yet. Nah. Yeah, let's have you do a couple, okay? So here's what I want. I want you to try these 2 problems. We can stop the video for just a second, and see how you do on these 2 problems. We'll keep them really simple. How about, I'll ask you to do this one, 27 to the 1/3 power. Like I said, we're keeping it simple. And the other one is going to be 125 to the 2/3 power. Okay? So it should take you about 2 minutes to solve these, if that. So pause the video right here, and we will take a look at them in a second. Okay, and hopefully you're back. All right, 27 to the 1/3 power. All right, this should be a pretty simple one. Remember, the top is the exponent, 1. When we raise them to the 1 power, it's just the same thing. And the bottom is the root. So this is the same thing as the cubed root of 27. And the cubed root of 27 is the same thing as the cubed root of 3 to the 3rd, because 3 times 3 is 9, times 3 is 27. And so then these cancel out, and I'm left with an answer of just 3. Look at this other one. This other one at least a little bit more complicated, but this is a good example of when, obviously you can see one situation would be way harder than the other, or hopefully you see that. So let's see here. I can look at this, and I can do this 2 different ways, okay? I could say, I want to take the cubed root of 125 squared, or I want to take the cubed root, that's a 3. I want to take the cubed root of 125, and when I get that, I want to square it. Now, I don't know about you, but off the top of my head, I definitely don't know what 125 squared is, besides being a big fat number, okay? So the last thing I want to do is square 125 to get some crazy big value, and then work backwards and try to find the cubed root of that insanely large value. I don't want to do that. I mean, clearly that number is going to be over 10,000. And so that, I don't know the cubed root of numbers over 10,000. That's just going to be a mess. And so that, while it's not wrong to do it that way, that seems like a train wreck. Okay. But I guess I shouldn't cross it out because, like I said, it's not wrong to do it that way. All right. So anyway, I just think that's going to be really tough. So let's try it a little bit different. And so for this, what I'd do is I'd say, okay, I like this other way, and go the cubed root of 125. Well, we just said that up here. We knew that the cubed root of 125 was 5, and then now all I have to do is square it. And 5 squared is, of course, 25. I like that a lot better. So basically, what value was this going to become? Well, it was going to become 25 raised to the 3rd power, which is a big number, okay? I think it's like, I don't know, 13,000 and something. Anyway, it's big. And so I don't want to work that way. I want to work this the easiest way I can. All right. Hey, let's look at another example. Okay. So where are we at? We're on exemple numero 4. And I'm sorry, I know your brains might be ready to pop, but we just got to look through at least 1 or 2 more, and then we will call it, okay? This might be able to be the last example, just to kind of, I don't know, help you get all the way there. So let's take a look at this. If I had something like, let's say, a to the 1/3 times a to the 7 thirds. All right? Now, this is really basic. This kind of goes back to just if I had something like x squared times x to the 4th. When we're multiplying two powers, what do we do with the exponents? Well, we add them. And so that would be x to the 6. So this is the exact same thing. We just have fractions. Now, fortunately, in this case, they gave us common denominators. But this is just a to the 1/3 plus 7 thirds. And 1/3 plus 7 thirds is just 8 thirds. Okay? So yes, that problem was meant to be easy. But we'll call that part A of this example. Okay? Now let's look at part B and make it at least a little bit more interesting. Okay? I could have something that says like a to the 2/5 times a to the 7/5 all over a to the 3/5. Okay, and let's take a look at this. So I could start with the top and say, well, 2/5 and 7/5 would give me a to the 9/5. And then on the bottom to have a to the 3/5. Remember, if I have one power over another power, like a to the 7th over, x to the 7th over x squared, I just subtract those and I get x to the 5th. So in the same way, we're just going to subtract these two. And 9 minus 3 is 6, so this becomes a to the 6/5 power. All right. Well, let's take it even another step, another level. Make this even more complicated. What if I had 2a to the 3rd power, b to the 4th power? And this whole thing was being raised to the 3/2 power. Okay, let's take a look at what that would actually do. And I want to try to simplify it all the way. Okay, so in this situation, what I would look at, I would say, well, that exponent kind of gets distributed. I don't know if that's really using that word correctly. I get nervous about saying it that way. But it gets distributed to each part. So that means that would be the same as 2 raised to the 3/2 power. And then a has already got that 3. And so remember, when you raise a power to a power, you multiply them. So this would be like a to the 9/2 power. And then b to the, I've got a 4 there already, so I multiply 12/2 power. Now the nice thing is that one of those fractions actually simplifies to a whole number. All right? It's the very last one. But so you say, well, 2 to the 3/2 power, what is that? Well, that's the same thing. Remember, the top is the exponent and the bottom is the root. So that's the same thing as the square root of 2 to the 3rd power. Okay? Times a to the 9/2 power times b to the 6th power. 12 over 2 is 6. And so I could look at this and say, well, what we're going to do right now is we're going to bump that, change this up a little bit and say this is the same thing as 2 squared times 2 times a to the 9/2 times b to the 6. And the square root of 2 squared cancel out, and the 2 comes out of there. So this whole thing simplifies down to 2 times the square root of 2 times a to the 9/2 times b to the 6. Whew, I know that one seemed pretty complicated. All right, now can you believe it? We're gonna go one more step, and so now you're gonna see Crazy Town in its full entirety. Here we go, ready? Let's take a look at part D. What if I said we're gonna have 2x to the 3/4? Now realize that that 3/4 exponent is only on the x, not the 2. Over y to the 1/3. I know, getting crazy, but we're not even close yet. We're gonna take the whole thing and raise it to the 3rd power. What? And then we're gonna multiply it by something else. Let's say y to the 4th over x to the negative, yes, negative 1/2. So now we've got fractions, we've got negatives, we're raising powers to powers, we got so much going on. But let's take a look at how we'd solve this. Okay, for that first part, I'm gonna use that word distribute again. I'm gonna distribute that exponent to every part there, okay? So what would that look like? Well, that would be 2 to the 3rd power times x to the 9/4 power over y to the 3/3 power. Okay, now that's nice because that bottom, that y to the 3/3 power, that's just y to the 1, y to the 1st power. Okay, and all this is still being multiplied by y to the 4th over x to the negative 1/2. Now, you kind of see that on the bottom there and go, well, wait a minute, I had this negative 1/2. I could kind of go back and just, do these 2 for 1 and simplify that and say, well, then this is the same thing as y to the 4th times x to the 1/2. The negative brought it up to the top of the fraction. All right. Now I can start combining things. Okay. So I could say I have, let's see here. I've got 2 to the third. 2 to the third is 8. I've got x to the 9/4 power times x to the 1/2 power. Well, x to the 9/4 times x to the 1/2. And then I've got y to the 4th over y to the 1 power. Now this y to the 1 and the y to the 4th up top, they kind of cancel a little bit out, and make that go away. There we go. And so what I'd look at and say, well, that'd be the same thing as y to the 3rd up top. The only other thing that's a little bit of a struggle is I got to have a common denominator here, but that's pretty simple. If I was adding 9/4 plus 1/2, I would just have to think about halves in terms of fourths. And so this would be 9/4 plus 2/4, which is clearly 11/4. So that's real simple. So the final answer is 8x to the 11/4, and then the y to the 4th over y reduces to a y to the 3rd. Woo! Crazy problem. Look how insane that was to start and how relatively simple it was to end. All right, and so with that said, what I'd like you to do is I'd like you to try just a couple more on your own, and then you're gonna go ahead and get started on your homework, okay? All right, so what I want you to do is I want you to try these 2 problems, all right? Let's try 3. So we're gonna do r to the 1/6 times r to the 5/6. Super easy. Then we're going to do a to the 3/5 times a to the 3/10. A little bit more interesting. And then we're going to end up with the quantity 27y, all being raised to the 1/3 power, times the quantity of y being raised to the 5/3 power. Okay? So those are the 3 problems I want you to try to work through. I'm guessing that first one's going to take seconds, second one's going to take a few more seconds, third one might take a minute or 2. So you can pause the video here and give a minute or 2, and then we'll give these a try. Okay, hopefully you're ready to go, and you see what I see on this first one, how easy it is. That just becomes r to the 6/6, which is r to the 1st, which is r. Simple. Okay, this next one, the first fraction is 3/5, the second one is 3/10. So the common denominator is tenths. So that would be the same thing as a to the 6/10 times a to the 3/10, and that's just a to the 9/10. So that's pretty simple. All right, and let's see here. Next, we've got 27y to the 1/3 times y to the 5/3. So this would be 27 to the 1/3, y to the 1/3 times y to the 5/3. Now the y's are real easy to combine here, but I got to remember that 27 is also 3 to the 3rd power. So 3 to the 3rd power being raised to the 3rd power. Remember, when you raise a power to a power, you multiply them. And 3 times 1/3 is just 1. And then when I get to the second part, y to the 1/3 times y to the 5/3, I add those and I get y to the 6/3. And so all of this works out to be whole numbers and actually comes out really clean, because 3, this 3 right here, times this 1/3 is 1. So this part becomes 3 to the 1st power. And then 6/3 reduces to just 2. So that becomes y squared. So the final answer is 3y squared. Yay. Super simple. All right. So now what I'd like you to do, we're going to talk about what we can do for homework. Unfortunately, I'm not there today. And so I can't look at your clock and see exactly how much time you have left. And so I'm going to try to give a homework assignment that's appropriate. But ultimately, guys, what I want is somewhere between 20 and 30 minutes of practice, okay? I need, if you're able to get just a little bit of this done in class, then I'm expecting at least 15 to 20 minutes of practice at home. I gotta have that. And so if I give too big of an assignment right now and you end up with like an hour of homework, that's too much. Don't do it. Okay, I'm not asking you to kill yourself on this stuff. I want you to do what's reasonable, okay? So hopefully use the rest of the time period in class, and then whatever you have left, when you go home, if you can tell me that you worked hard for 20 straight minutes, maybe even a half hour, once you get to that point, call it quits and you can be done. So I'm gonna give a really hefty size homework assignment right now, but with that catch, that if you can say, man, I went home and I worked hard for a half hour straight, but this is all I got done, well, then we're good, okay? I'm saying that that's fine. But with that said, what I'd like you to do is I want you to go back to number 17, okay? So remember, we're on page 29. And I want you to go back to number 17. And I think that those are just some pretty simple problems that would be good to kind of work the other parts. So we're going to go back to 17, and we're going to work parts B and C as well on those. And what we're going to do is we're just going to keep rolling through this whole section. Because like I said, I just want to see you get practice. And so we're going to do, I know this is going to sound insane, but we're going to do 17 through 55 odd. Okay? Some of those problems have a couple parts, most of them don't. Okay? A lot of 25 through 49, that's just all one part each. And so that should be relatively simple. But I want you to do 17 through 25 odd. If you finish this in class, yay. If you have to take it home, I'm sorry, but I do want you to practice. If you get stuck at home and you have more than a half hour of work, please call it quits at a half hour. All right? You guys have a great day. Thank you.